let's talk now about the causes of global warming and why the greenhouse gases warm the planet. So to begin our conversation, to understand what's going on, first we have to understand some vocabulary words, okay? Some vocabulary words about radiation. Radiation is another word for light. Technically speaking, light is radiation that our eyes can see. But there are some forms of radiation that our eyes cannot see. You know how, like a dog whistle, only dogs can hear it? Their ears are sensitive to different frequencies of sound than a human's ears. There's also frequencies of light. The colors of the rainbow, yeah? Have you ever heard of Roy G. Biv? Who is Roy G. Biv?
It's red, orange, yellow.
Yeah. Red, orange, yellow, green, blue, indigo, violet, right? Those are the colors of the rainbow, and those are different frequencies of light. Different frequencies of light correspond to different energies of light. Over here on the wall, I have a poster of the electromagnetic spectrum, okay? And on this poster is the whole spectrum of radiation. Just like in visible light, the spectrum is Roy G. Biv. But if you go beyond violet, which the V in Roy G. Biv stands for, purple, if you go beyond violet, what's there? Ultraviolet. The word ultra means beyond. And if you go below red, the root infra means below. Now we're in infrared radiation. We do not see infrared radiation. We do not see ultraviolet radiation, but we know it's there. Infrared, if you stand in front of a fire and you feel the warmth of the fire, you are feeling the infrared radiation from the fire. And if you go outside and you get a sunburn, you are experiencing the ultraviolet rays of the sun. Our eyes don't see them, but we know they're there. And it turns out there's even more than that. This very narrow little spot, you might not even be able to see it from over there, that's just the range of the whole spectrum that our eyes can see. Outside of that, we have infrared. Now, if I go to the left on the poster of the visible light, that is energy that is lower than visible light. So infrared, even though it feels warm to us, the energy of the waves is actually less than visible light. And if you go even lower than that, is microwaves. And you might say, wait a minute, I can cook my food with microwaves. How can it be lower energy? If you have the same size wave of microwave as you do of light, the energy will be lower. Okay, we're going to talk, electromagnetic spectrum is a whole unit for us in the spring. For now, I'm just giving you the basics because we need to have a small understanding of it to talk about global warming and how global warming occurs. Okay, and then below microwave is radio waves. We know radio waves are all around us, right? You can go anywhere and turn on your radio and get a station. That means the radio waves are in the air, but we don't notice it, we don't feel it. They're low energy. Ultraviolet rays, on the other hand, are much higher energy, and we do know they're there, because if you stay outside too long, you get a sunburn. And beyond that are X-rays. X-rays, we know, are very high energy. Large doses of X-rays will give you cancer, right? And then gamma rays can kill you, but thank goodness our atmosphere blocks the gamma rays. So now let's talk about some vocabulary words. You can see me, you can see everything in this room. How do you see something? Because light is entering your eye, right? So if light comes from this light and hits her hair, how does it get to our eye? There's a word that we say, the light, it's a word for light bouncing off of something. Reflect. Yes, very good. Okay? So, let me think about the form of the word I want to use. Reflective. We say the surface that the light hits is reflective. Okay, so that's one word, or that's one. There's four things the light can do when it hits a surface. That's the first thing. The next thing is this window, the light hits the window and it comes right through, doesn't it? I know that because I can look outside and I can see what's on the other side. So we say that window is transparent. Okay. The next one is, I take this piece of paper, I hold it, you see it got brighter. Yeah? That means light must be passing through it, but I can't see what's on the other side. There's another word that's similar to transparent. Translucent. Translucent. So things that diffuse light the word diffuse means to spread out. And the last one is, if the window lets the light through, the blind or the shade it blocks the light. What's the word for that? Opaque. Opaque. Starts with an O. Okay. So these four things that can happen to light play a very important role in what happens with global warming. So first, let me start off with radio waves. Here's my radio. Sorry, it's in two pieces. The speaker. Anyway, this is my radio. I'm going to turn it on.
Everyone's struggling in capacity, and
okay.
so folks have that willing to talk.
So I know the radio waves are coming into the room, and my radio receives them. Light is not coming through the ceiling, is it? So the ceiling in the building must be opaque to visible light. But what do you think it is to radio waves? Yeah? Otherwise the radio waves wouldn't come into the room. Check this out. I've got this box. Okay? This box is lined with aluminum foil. I'm going to put my radio inside the box. Turn it on. You can see it's already not doing very well with the, but if I do this, it completely turns off. So what do you think aluminum foil is to radio waves? Opaque. See that? So now that's a good demonstration for transparent and opaque. So let's show you another one. First of all, before we show you this video clip, I just want to show you some pictures, which means I need to turn my projector on. Here we go. This first picture I love. We have an infrared camera. Okay? So an infrared camera, your phone takes pictures with visible light. A normal camera takes pictures with visible light. An infrared camera, you can probably guess, can see infrared. And it takes that infrared image and it changes it to visible light, and certain colors of visible light represent certain temperatures. So infrared is the type of radiation that is given off by things that are hot. Any temperature gives off infrared. The hotter it is, the more infrared it gives off. Even ice cubes give off infrared radiation, but it's a lot less than a pot of boiling water. Okay? So the camera, the infrared camera, takes a picture in the infrared and allows you to see temperature. So when I look at this picture, I see the walls of my living room are blue. That's the coolest part in the room. Let me also tell you, this camera, it does take a little bit of visible light as well, so that it allows you to see and understand what you're looking at. This poster in my house, if you looked at it only with infrared, it would all be the same color because it's all the same temperature. So the fact that you can read the poster and see the picture in it, that's because there's some visible light in the camera as well. Okay? But these colors, that's from the infrared spectrum. So my walls are cool. This is my television that's been on for quite a while. And you can see the white, that's the warmest. The red is almost as warm as the white. But then if it's not quite that warm, it's green. And this right here is my son sitting on the couch who's watching television. So his body, 98.6 degrees, right, or close to it, is very warm. This is where the cable box is under the TV set that's been on for a while. It's warm. And what I like the best about this picture, what I think is so cool, is that, you know, hot things rise, right? Heat rises. And so the heat from the television has been rising, and it's caused the wall and the ceiling to warm up. And now I can see that the temperature of the wall is greater above the TV because of that rising hot air. Now when you look at the wall above your TV with your eyes, you can't see that, right? That's because our eyes don't see infrared. But with the camera, we can see that. Okay, so now let's take a look at a short video clip.
Infrared light also has a lot of really interesting properties that visible light doesn't have. For example, it can often pass through things that block visible light entirely. I have a black plastic bag, and as you'll notice, you can't see through it at all. But with an infrared camera, there's no problem. But just like infrared light can penetrate some things that stop visible light, it also gets stopped by some things that let visible light through. For example, here's a piece of glass. And as you can see, none of the infrared gets through at all.
Okay, a piece of glass. So a piece of glass is transparent to visible light, but it's opaque to infrared, right? I cannot see the heat of her face. It's not coming through the glass, okay? And I can tell from the camera that the piece of glass is cool. If the glass was warm, it would shine red like her face, okay? But this piece of glass is cool. So that leads us to greenhouse gases. A greenhouse, I think everyone knows what a greenhouse is. What is a greenhouse made out of? If you went up to a greenhouse and what are you knocking on? Glass. That's right. So glass is transparent to visible light. That's energy. All radiation is energy. That energy enters the greenhouse, it hits the surface, and it is absorbed. I forgot to write that. When things are opaque, that's what's happening to the light. When things are opaque, the energy is absorbed. There's a very important law of physics called the law of conservation of energy. The law of conservation of energy does just what the words say. Energy is conserved. When energy is conserved, that means it doesn't go away. It's always there. It doesn't appear out of nowhere, nor does it disappear into nothingness. It's always there. But what can happen is it can change forms. So energy from the sun comes down in the form of light. Then it's absorbed. What do you think it becomes then? The energy is no longer light. Now it's called thermal energy. And thermal energy, what thermal energy is all that's happening is the molecules in the whatever it is start to vibrate more. The hotter something is, the more the atoms vibrate. And that's why they give off infrared radiation, because vibrating atoms give off infrared radiation. And so that thermal energy now can become infrared energy. So the amount of energy has always been there, but it just changed from light energy to thermal energy to infrared radiation energy. Now sometimes when light is absorbed, it gets used and transformed into other types of energy. Like a tree, for example. The light is absorbed by the leaves on the tree, and the photosynthesis process turns that light into plant energy, right? If you want to call it that. And when you get hungry, you say, hey, I'm going to eat a salad. Now you've taken the energy that's in the plant and you've put it in your body. And now it's stored in your muscles. And now I can pick this pen up because of the breakfast that I ate this morning. And now the energy that I had in my arm is now stored in the potential energy, we call it, of the pen. All this stuff we're going to talk about later in the year. These are all topics that we're going to discuss more deeply. And now if I let go of the pen, woohoo, it speeds up, and the energy becomes motion, energy of motion in the pen, and then it hits the floor, and it becomes energy of sound, and you hear it. And because it's smacked on the floor, now the atoms in the floor are vibrating more, and it's become thermal energy, and now that thermal energy gives off infrared. And so what we're going to learn about today is the energy coming in from the sun needs to equal the energy that's leaving planet Earth. And we call that the energy balance. Okay? We call that the energy balance. What if there was more energy coming in than there was going out? What do you think would happen to the temperature of the Earth? Sure, it would increase. And if more energy was going out than was coming in, the temperature would decrease. And if they were the same, the temperature would stay the same. So I'm going to use an analogy here that hopefully will help you understand a little better what's happening with global warming. Imagine you have a big container, like a giant 55-gallon drum. Okay? I would set this up as a demonstration, but it would be too wasteful of water. So I'm not going to set up the demonstration. In fact, instead of drawing it on the board, I have a nice picture of it. So let me just quickly. So here's my giant bucket, and I drill a hole in it. Okay? And I get my hose and I start pouring water in it. And I fill it all the way to the top, and then I turn the water off. This water would be shooting out really fast, right? If you swim down to the bottom of the deep end of the swimming pool, you feel that pressure on your ears, don't you? So that pressure is shooting that water out really fast. But then, as the water level gets lower and lower and lower, what happens to this stream of water? It gets less and less and less, right? Until when the water is very shallow, it's just barely coming out, right? So if this water out is more than this water in, the level of the water in the bucket is going to get less, yeah? And if this amount of water in is more than this amount of water out, of course, the water level rises. But if we keep this the same always, you can see that if the water level rises, this is going to get more and more until eventually this amount of water in is going to equal that amount of water out. And when that happens, what happens to the level of the water in the bucket? It's going to stay the same, right? We call that situation equilibrium. So when the amount of water in equals the amount of water out, we say it's at equilibrium, and the water level stays the same. Now let's use our analogy to talk about the temperature of the Earth. Here comes the sun. That's the water in, but it's energy in. It is absorbed by the Earth, and now the Earth wants to get rid of that heat through infrared radiation. And so the energy leaves the Earth. If they are the same, then the Earth is in equilibrium and the temperature stays the same. By the way, I should mention, planet Earth, even though we live in the atmosphere of planet Earth, beyond the atmosphere of planet Earth is the vacuum of space, right? Energy cannot like when you touch a hot stove, woo, I burned myself, right? The heat went right from the stove to your hand because you touched it. It was a transfer of energy because of contact. But the Earth and its atmosphere, what are we in contact with? The vacuum of space? No, there's nothing there. So heat cannot leave the Earth through the same way heat moves into your hand from a hot stove. The only way heat can leave the Earth is in the form of radiation, infrared radiation, light. Radiation can travel through the vacuum of space. How do I know that? Because light from the sun reaches us, doesn't it? Light from the sun travels through the vacuum of space and reaches the Earth. So the only way this can happen with energy from the Earth is if it's in the form of radiation. And if it has been absorbed by the Earth, then that's going to be infrared radiation because it's given off Remember, infrared is given off by things that have temperature, okay? All right, so what happens? The light comes in. I started to talk about the greenhouse and I got sidetracked. The greenhouse is made of glass. The light comes in, it's absorbed by things inside the greenhouse. They get warm and they emit infrared radiation. But what happens? The infrared radiation is absorbed by the glass because the glass is opaque to infrared. And what happens to the glass? It gets warm. Now, if something is warm, it gives off infrared radiation, right? So you might say, okay, the glass got warm, now it's going to emit infrared radiation outside the greenhouse. You are correct in saying that. But it doesn't only emit it back out of the greenhouse. Where else does it emit it? Inside the greenhouse as well. So if the glass wasn't there at all of the infrared would go that way. But with the glass there now, part of it goes that way, but part of it comes back. And that's why the greenhouse gets warm. Warmer than outside. Same thing happens to your car on a sunny day, right? You park it in the sun, the light comes in the windows, heats up the dashboard of your car. The dashboard of your car is warm now, so it gives off infrared, and it is blocked by the windows. Next time you park your car in the sun, go up and feel the window of your car. It's going to be very warm.